All right, everybody. So we're going to do 3.4 electron spin, and I have already filled in some of the notes because I don't want to just write in front of you because that takes a really long time. So there may be points where you have to just pause the video and write what I have written first and then add on what I'm going to add. So spinning electrons cause magnetic moments. So if things are attracted to a magnet or interact with a magnetic field, it has something to do with how the electrons are distributed in that atom. And when scientists started looking into magnetic moments, what they found was that there are these two equal and opposite magnetic moments that are possible. And this is for an electron. And so when we look at an electron, how we indicate these two equal and opposite magnetic moments is spin up and spin down. For right now, all that really matters is that if two electrons are in the same orbital, which we're going to talk about what that is, they're just going to spin in opposite directions, and we're going to call one of those directions spin up and one of those directions spin down. If a subshell contains one electron of each type, they will cancel each other out and provide no overall magnetic moment. So if I'm trying to fill in an electron or an orbital, hydrogen only has one electron and it's in the 1s orbital. And remember, if you're not sure, you can look back up at the periodic table and see what block does hydrogen reside in. So hydrogen only has one spin up electron. Helium has two electrons. One of them is spin up and one of them is spin down. So helium has what's called an electron pair. So this is an unpaired electron. There's just one spin up, or it could be one spin down. Just commonly you do the spin up one first. And then helium has an electron pair in its 1s orbital. If you have an atom with an equal number of spin up and spin down electrons, or they're all paired, that's a diamagnetic atom. And again, that just means all your electrons are paired, so you don't have any individual ones. If there are unpaired electrons, the atom is attracted to a magnetic field, and it's known as a paramagnetic atom. So again, paramagnetic is unpaired. You've got to be careful. There's a little bit of a trap here. Sometimes people see para and they try and make that into paired, but it is not. So paramagnetic is the unpaired electrons. The greater the number of unpaired electrons, the greater the magnetic moment. So we're going to be doing a lot of different orbital diagrams on this thing, and in each situation I'll let you know whether that atom would be diamagnetic or paramagnetic. But if we go back up here to hydrogen, hydrogen has an unpaired electron, so hydrogen is paramagnetic, which I'm just going to write paramag for the sake of time. And helium, because it has both of its electrons paired up, is diamagnetic. Okay, so now we're going to learn how do we turn an electron configuration, which we learned how to do in the last section, into an orbital diagram. So orbital diagrams look like this. This is an orbital diagram. Normally they start in the opposite direction, so like they start with the 1s and then they fill up, but I just kind of wanted to put some things over here on the edge to show you. So orbitals are exciting. What we learned in the Pauli exclusion principle is that an orbital, so all these scientists did all this stuff, an orbital can contain a maximum of 2 electrons. So if I wanted to figure out how many orbitals each subshell can have from my photoelectronic spectrum, I can then split up the total number of electrons that whole subshell can hold into orbitals. So from our photoelectron spectrum, every single s subshell always is 2 electrons high, or it holds 2 electrons. And so it is only going to have one orbital because each orbital can contain 2 electrons. So my s orbital would have 1, 2 electrons, and those electrons would have opposing spins. My 2s orbital, again, every single s orbital on a photoelectronic spectrum is always 2 electrons high. Every s subshell can contain 2 electrons, so they have 1 orbital in them. Your 2p subshell on a photoelectronic spectrum can hold 6 total electrons, and so then to decide how many orbitals there must be in the 2p, each orbital can only hold 2. If I need 6 total, I will need 3 orbitals. So I have 3 different orbitals. Each one of them contains 2 electrons spinning in opposite directions. That's 6 electrons total. And then if I get into my d orbital, the d orbital or the d block or the d subshell, however you want, sorry, the d subshell or the d block, not the d orbital, has 5 orbitals in it. And each one of those can hold 2 electrons because every orbital can only hold 2 electrons. So the d block is 10 columns long. The d subshell can hold 10 electrons. Divide that by 2, you have 5 orbitals. And then the last one, which we don't do very often, but I'm putting these little ellipses for a break, is for F. The F block is 14 atoms long, or has 14 columns in it. And if you did a photoelectronic spectrum that had an F subshell in it, it is 14 electrons high. So if I divide 14 by 2, that's 7. So 1, 2, 3, 4, 5, 6, 7 orbitals. And then those 14 electrons would be distributed in those orbitals, 2 in each orbital. Just like all of this. So our orbital contain a max of 2 electrons, and those 2 electrons must have opposing spins. So you'll notice that all the arrows that I put in have one that's spinning up and one that's spinning down. So how do I know how to fill these up and in what order? That's going to be based on the Aufbau principle. So in the ground state of an atom or ion, our electrons are going to fill the lowest available electron level before filling higher levels. The lowest available electron level is not always obvious because not all of the subshells have the same amount of energy. So like an S and a P shell are not energetically equivalent. So the way to remember them is this little drawing that I'm going to do over here on the margin. I included this picture so that you could kind of visualize what I'm doing a little bit, but you obviously don't have this picture in your notes. You're just going to do what I'm doing in the margins right now. So from a photoelectronic spectrum, we have 6 total energy levels for every atom on the periodic table. In the first energy level, or the first row of the periodic table, there's only an S block. In the second energy level, there's an S and a P subshell. In the third energy level, there's an S, a P, and a D. And in the fourth, it's an S, P, D, F. When you're learning how to do these, you just add 1 letter for each energy level, so not too bad. And then there's no more than F, so once you get to the F's, then you just keep going with that. And then the way in which the orbitals fill energetically is shown in this diagram, so you can kind of visualize it a little bit. You'd have to like follow the arrows, so you would go from the 1s to the 2p to the 2s to the 2p to the 3s to the 3p, 4s, then back to a 3d, 4p, 5s. So that's a way of visualizing it. If you draw this diagram on your AP test or on anything that you're working on, you go in diagonals. So I fill the 1s, and then I come in, I fill the 2s, and then I come back and fill the 2p and the 3s, and then I come back and I fill the 3p and the 4s before filling the 3d and then the 4p and then the 5s, et cetera, et cetera, et cetera. So you just kind of keep scrolling down through each one of these little situations to figure out how you're going to fill your thing. So then we're at Hund's rule. So because electrons repel each other, every orbital in a subshell needs to contain one electron before you start doubling them up. So we're not gonna pair electrons together until every orbital has one electron. So we're gonna kind of combine all those rules together to show you how I would go from an electron configuration to both a photoelectronic spectrum and to an orbital diagram. So we're going to do this for two atoms. We're going to do it for vanadium, and we're going to do it for magnesium. So vanadium's atomic number on the periodic table is 23. The number of electrons in a neutral atom of vanadium would then be 23. If it's got 23 protons, it needs to have 23 electrons to be neutral. Vanadium is in the fourth row or the fourth period of the periodic table, and rows and periods go left to right. So I'm talking about, up like where it's at. It's in the D block of the periodic table, and if I look on my periodic table, it's in the 3D. So that's when I'm writing my electron configuration, my final electrons should be in the 3D block. So I'm going to use my little diagram that I sketched over here. So I'm going to fill the 1s first, then I'm going to fill the 2s, then I'm going to fill the 2p and the 3s, then I'm going to fill the 3p and the 4s, and then I'm going to stop here at 3d. So I know that every s thing that I go through has 2 electrons. If I filled 1s, that's 1s2, 2s2. I know that every p orbital has p subshell, so confusing. Every p subshell has 6 electrons. So if I've gone through it, that means it's full. Then I get to my 3s. Every s subshell contains 2 electrons. 3p, every p subshell contains 6 electrons. Then 4s is the next thing I've filled if I'm just following my squiggly line. 4s has 2 electrons, and then I'm ending in the 3D block, so then I actually have to look at vanadium and I have to count how many atoms over vanadium is. So vanadium is the third electron in the D block, or third atom in the D block. Wow. Third atom in the D block, so it's 3D3. If I'm going to draw a photoelectronic spectrum for anything, I want to look at what energy levels exist so that I know where to put my line breaks. So I have a 1s, I have 2 as energy levels, I have the third energy level, and I have a fourth energy level. So I'm going to put 4 breaks, 1 for each energy level. So this is going to be my 1s, this is going to be my first energy level, second energy level, third energy level, and then my fourth energy level will be at the end. So first energy level, second energy level, third energy level, fourth energy level. Or if you're thinking about the shell model, this would be like the shells. So in my first energy level, I just have a s orbital and it's too high. In my second energy level, I have an s and I have a p, so I should draw my p 3 times higher to show that there's 6 electrons in there. Then I have my 3s2, 3p6, so same height as the last one. Then I technically fill my 4s before coming back to my 3d, which is 10 electrons tall, so 5 times as high as my s orbital. And then I have, but it's only 3d3. Jeez. So my 3D comes back here, but it's only 3 high, so it should only be like 1.5 times as tall as my 3s. So if I label this, these are all s's, these are p's, and then this is my only D block, and it's short because there's only 3 electrons in the D for my electron configuration. Okay. Then lastly, I'm going to draw my orbital diagram. So I got a 1s, I got a 2s. I'm just doing them in the order of the electron configuration. I have a 2p, and I know that since there's 6 electrons there and each orbital can only hold 2, I need to have 3 orbitals. I have my 3s, can only hold 2. I have my 3p, 1, 2, 3. I have my 4s, and then I have my 3d, 1, 2, 3, 4, 5 in the d block are available. If the orbitals are full, then I just pair up all the electrons, spin up and spin down for every orbital that's full. And then in my 3D, I have 3 electrons, and I have to put them into individual orbitals first because of Hund's rule. So every orbital in the subshell needs to contain 1 electron before you start doubling them up. So each one of those electrons needs to go in its own orbital, and I would only start doubling electrons in the d orbital when I had 6 electrons there. Okay, one more and then we are done. So if we're looking at magnesium, magnesium has the atomic number 12. It has 12 electrons. Magnesium is in the 3rd row of the periodic table, and it's in the 3s block, so that's where I'm going to end when I'm drawing my electron configuration. So I can just do my 1, 2, 3 energy levels, S, 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 P, and P, and then my S could also have a D block. Then I'm going to think, how am I going to fill it up? So I'd fill up the 1s, then I'd fill up the 2s, then I would fill up the 2p, and then the 3s, and then that's where magnesium is. So then I'm done. So I went all the way through my 1s orbital, so that's full. I went all the way through my 2s orbital, so that's full. I went all the way through my 2p, I should not say orbital, I should say subshell. I went through my 2p subshell, so that's full, and my 3s subshell is also full because magnesium is the second atom in the 3s row. Wow, so many ways. So I'm going to have, in my photoelectronic spectrum, I'm going to have 2 breaks. So I'm going to have my first energy level in the first break, my second energy level in the second break, and my third energy level in the third break. So 1s2, here we go, 2s2, 2p6, and then 3s2. That would be what its photoelectron spectrum would look like. And then if I do its orbital diagram, I have to put all of the orbitals that are in my electron configuration, and then all the subshells that are in my electron configuration, and then the number of orbitals that I draw is however many are necessary to get that number of electrons in. So every orbital can hold 2 electrons, so 1s just has 1 orbital, and that's true of all the s blocks. And then p, that subshell, has 6 electrons, so you'd need 3 orbitals. The number of times I have mixed up the word electron, subshell, and orbital in this video is incredible, and I apologize. Okay, so then I just have to distribute these all out based on my electron configuration. So I've got 1s2, 2s2, 2p6. Each one of these arrows is an electron. And then my 3s2, those are paired up. And then the very last thing we're going to do is we're going to decide is magnesium and vanadium paramagnetic or diamagnetic. So if all of your electrons are paired, that's a diamagnetic atom. So magnesium would not interact with a magnetic field. Everything is paired up. If I look at vanadium, I have 3 unpaired electrons. So this would be a paramagnetic atom, and it would interact with a magnetic field or respond if you held a magnet next to a piece of pure vanadium. They would be attracted to one another. All right, so that's our video. Sorry for my large number of verbal slip-ups, but there you go. And then you're going to do the orbital practice page that's also on this same link on Canvas. All right, thanks. Have a great weekend.